All right, let's work some examples here. The first 5 or so examples that we're going to do here are going to be exceptions to the octet rule. I told you in an earlier video that if there were exceptions to the octet rule, I would point them out. And so as we're going through here, I will point those out to you in each of these molecules. So I would encourage you I think after the first couple ones here, I think we'll go ahead and do these first 2 together, and then the next few, I would encourage you to pause the video before I work through them so that you can see if you have gotten the hang of doing it, understanding when the exceptions are, or how to deal with the exceptions to the octet rule. So the first one here is boron trifluoride. Boron is going to be the central atom here, which is not the thing that is breaking the rule. That would be the normal setup, because boron has 3 unpaired electrons and fluorine only has 1. What's going to be different is that boron is not going to follow the octet rule. It is not going to end up with 8 electrons around it. If we add up the electrons that it's going to have, or its valence electrons anyway, you get 3 from boron, plus 3 times 7 from fluorine. This fluorine is in column 17. And so we're going to have 26 electrons total. Or sorry, 24, not 26. 24 electrons total. And so if we look at our skeletal structure here, we have 6 already in the single bonds. So then we have 8, 10, 12, 14, 16, 18, 20, 22, 24. We have run out of electrons, and we do not need to make a double bond to the boron, because like I said, the boron is going to break the octet rule, and it is going to break the octet rule by having less than 8 in this case. So we're not going to form 2 different double bonds to try and get it to be more. If you remember, because boron is so small, it will tend to break the octet rule by having fewer than 8 instead of more. Right, in this one, there's actually 2 things that I need to tell you. Number 1 is that xenon is going to be central. And I would have to tell you that because xenon has no unpaired electrons, and fluorine has 1. So our rule that the thing with the most unpaired electrons goes in the middle, that rule is broken by this molecule. And I will need to tell you that xenon is going to break the octet rule. It actually already has 8 just from the fluorines. But if we look at the total number of valence electrons, xenon is going to have 8 valence electrons. It's noble gas, so it has a full octet. And then we're going to have 4 times 7 from the fluorines, so that's 28 plus 8, which gives us 36 electrons for the whole thing. And now we're going to get some good practice counting by 2s. So we have 8 already in there. If we just pick a fluorine and start putting them in, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. The fluorines are now full up, and we still have 4 more to go. And so the last 4 are going to be lone pairs on the xenon. We are not, I repeat, we are not going to put double bonds to the fluorines, because if we did that, then the fluorines would also be breaking the octet rule. And it is just the xenon that is going to break the octet rule. And in this case, it has 4 more electrons than an octet, but it is capable of doing that. Xenon can do that. All right. So with that in mind, go ahead and try to work out the proper Lewis structures for these 2. The sulfur is going to break the octet rule in this molecule, and in this molecule, the phosphorus is central, and it will break the octet rule for the best structure. It's possible to draw a structure that doesn't break the octet rule, but the best structure will. So go ahead and give that a go. Alright, so in this molecule, we have 6 sulfurs, or sorry, not sulfurs, 6 fluorines attached to 1 sulfur. I didn't really get them evenly spaced there, but I think you get the idea. If we add up all the electrons, we have 6 from the sulfur, and then 6 times 7 from the fluorines, so that is going to be 48 electrons in the whole thing. And here we go. We already have 12 in the single bonds, so 14, 16, 18, 20, 22, 24. Kind of gets scrunched in there, but 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So we fill up the fluorines. We have enough to do that, but we do not have any left over. And so the sulfur, just through having 6 single bonds, is breaking the octet rule. And that is the Lewis structure for sulfur hexafluoride, which is the gas that I breathed in that video that I put up, and it gave me a really low, really low sounding voice. That was sulfur hexafluoride. Right, for this one, if you remember, I said the phosphorus was going to be central. So we're going to put everything else attached to the phosphorus. If we count up the electrons that we have available, oxygen has 6 valence electrons, phosphorus has 5, and then we have 3 bromines, which have 7 each. And so that is, let's see, 21 plus 5 is 26, gives 32 electrons. I'm going to start putting them on the oxygen because that's the most electronegative of the elements. And so I'm going to have 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Alright, so I've put in all of the electrons, and at this point everything has an octet. And so this is an acceptable structure, but if you remember, I said that the best structure would have phosphorus breaking the octet rule. And if we look at the formal charges on these, and I won't calculate all of them up right now, but the bromines are going to have 0 for their formal charge. The oxygen is going to be -1. It has 6 valence electrons. It has 6 just in the lone pairs, and then 1 from the bond, which gives it -1. And the phosphorus is actually going to be +1, because it has 5 valence electrons, but it's only assigned 4 from the single bonds. And so in order to make the best structure, we would take one of those lone pairs from the oxygen and make a double bond to the phosphorus. This would give phosphorus 0 as its formal charge because it has 5 valence electrons and it has 5 bonds, and so it would have 0 as its formal charge, and then the oxygen would also be 0, with 4 from the lone pairs and then 1 from each of those 2 bonds. Alright, so then the last one here for the exceptions, for now at least. Go ahead and pause the video here after I tell you here that the phosphorus is going to break the octet rule, which you can kind of already tell because there's going to be 5 chlorines attached to it, as it is the central atom. So go ahead and give that one a go. Alright. So we have our phosphorus in the middle of our molecule. We have all 5 of the chlorines attached to it. So already it is breaking the octet rule. If we count up our valence electrons, we have 5 plus 5 times 7. It's going to give us 26 electrons. And if we put in the lone pairs on the chlorines here, we'll just pick one and go with it. So we have 10 already in there. So 12, 14, 16, 18, 20, 22. Oh wait, I miscounted that. Okay, yeah. It's not 26. That is 35. Where did I get 26? Oh my gosh. Okay, so I have 35 there plus 5 would be 40. Phew. Okay, yeah, 40 electrons. Am I doing that right? I think so. Yeah, that should be right. Okay, so where was I? Sorry about that. So we have 10, and then we had 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. There we go. Much, much better. How did I get 26? I don't know. Anyway, this is the correct Lewis structure. So as you can see, all the chlorines have their octets, and the phosphorus, just from having the single bonds, is breaking the octet rule. There's no need to make a double bond to any of the chlorines, because if you check the formal charge, phosphorus is at 0. It has 0 formal charge with those 5 bonds. So it is okay. All right, let's do a few more here. These are not going to break the octet rule. So this one, nitrogen is going to be in the middle because it has the most unpaired electrons. If you add up the electrons, see if I can do it correctly this time. We have 5 from the nitrogen, 3 times 7 from the fluorine. This time it is in fact 26 electrons. And so if we add in the electrons to the fluorines first, again, terminal atoms first, so we have 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We still have 2 left after filling up the fluorines, and so those are going to go on that nitrogen. This one is similar to ones we've seen before as well. Both of the carbons have a equal right to be in the center of the molecule, so we'll put them both in the center and just make it as symmetric as possible. And that's what we get from that. If we add up the electrons, 2 times 4 plus 2 times 1, 4 from each carbon, 1 from each hydrogen. That gives us 10 electrons total. And so if we look here, we already have 6 in the single bonds. So we'll just pick a carbon and put some in. 6, 8, 10. Very similar to what we saw before. This carbon has its octet, but this one is very angry with us. And so to make them both happy, we will move those lone pairs to give us to give both of them their octets. And this is acetylene. If you've ever used an acetylene torch, that is what you're burning in that. Okay, here's a little bit something a little bit different here. What's wrong with this molecule? And what's wrong with this molecule? There is something wrong with both of these structures. So go ahead and pause the video and see if you can work out what's wrong with each of these. One of them is a little bit easier than the other one, but they do both have something wrong with them. So go ahead and pause the video. So this one, I think, is a little bit easier to tell what's wrong. This carbon does not have an octet. And so to fix this one, we would move one of these double bonds down, or one of these lone pairs down here to make a double bond. So we'll just say it's that one. And so that would be the correct structure. I believe that's formaldehyde, I think. But I could be wrong about that. So that would be the correct structure. This one is a little bit tougher, because if you notice, It has an octet, both of them. Both of the atoms have an octet. We have 8 electrons, 8 electrons. So it should, it seems like it looks fine to me. But how many valence electrons does nitrogen have? That's 5. We have 2 of them. So there should be 10 electrons in this structure. If we count them, we have 2, 4, 6, 8, 10, 12. We have too many electrons. We need fewer electrons. This molecule could theoretically exist, but it wouldn't be N2. It would be N2 2 minus is what it would be. So we would need to get rid of one of those lone pairs, but now this nitrogen is unhappy, and so we would need to move one of the lone pairs over here to make a triple bond, so that now both of them would have their full octets. So need to be careful when we're counting electrons. Hopefully you won't make quite as egregious of a mistake as I did back here, where I was somehow off by 14. I guess I thought I had 3 chlorines instead of 5. But anyway, be careful when you're counting electrons, because it can lead you astray if you're not careful with that. Alright, so the last thing here that we're going to do in this video anyway is writing the best structure for CH2O2 and then the best structure for sulfuric acid. So for CH2O2, we have some choices here for how the skeletal structure is arranged, because it might seem like you would have the molecule arranged like this, because there's room for 4 things to attach to the carbon, and we have 4 things other than the carbon, which would be in the center. But if you try to get this to work, you will never be able to get a structure with 0 formal charges, with everything attached to the carbon. So instead, we are going to have one of those hydrogens attached to an oxygen. Now, this is something that I would tell you beforehand. I would tell you that one of the hydrogens is attached to one of the oxygens, and that would probably be how I would explain that to you, just because otherwise you'd be working yourself for 20 minutes trying to figure out how you could get that thing arranged properly. There's no way to get it to 0 formal charges with everything attached to the carbon. But with the hydrogen attached to the oxygen, it is possible. So if we add up the valence electrons here, we're going to have 2 from the hydrogens, 4 from the carbon, and then 12 from the oxygens, which is going to give us 18 electrons total. We already have 8 in the structure, so we have 10 more to give. So 10, 12, 14, 16, 18. So we have run out of electrons. Carbon is still unhappy. Theoretically, we could make a double bond to this oxygen, but if you work out the formal charges on that, this oxygen is not going to be very happy. Right now, this oxygen has a formal charge of -1. And so to get our full octet for the carbon, we will move this lone pair down here. So we'll just cross that one out. And this is the best structure for that molecule. Sulfuric acid, on the other hand, is again a slightly more complex molecule, because we're not going to have just a central atom and things attached to it. We're going to have things tertiary, or I guess secondary, to that central atom. And so what I mean by that is we're going to have the sulfur in the middle, and we will have the 4 oxygens bonded to it, and then we're going to have the hydrogens attached to the oxygens. And that's explained here in the text as well. And so again, the best structure here is going to have 0 formal charges. If we add up all of our electrons, we get 2 from the hydrogens, 6 from the sulfur, and then 24 from the oxygens, which is going to give us 32 total electrons. If we start putting those in on the oxygens, we already have 2, 4, 6, 8, 10, 12 in the single bonds. So starting from there, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've used up all of our electrons. But if we check the formal charges here, even though everything in the structure has an octet, both of these oxygens have -1 formal charges, and the sulfur has +2 formal charge. So the sulfur has 6 valence electrons, and it has no lone pairs and only 4 bonds, and so it is +2. It's very angry. And so the oxygens being -1 is not great either. So how would we fix this? If you want to try and figure it out on your own, I encourage you to pause the video and see how you could fix this structure to get 0 formal charges for everything. The way that we're going to do that is by taking a lone pair from each of these oxygens, not 2 from one from each of these oxygens that aren't bonded to hydrogen, and make a double bond to the sulfur. So the sulfur here is breaking the octet rule, and it is going to end up with 0 formal charges because it has 6 bonds, and so we would have 6 minus 6. And the oxygens are also going to end up at 0. So that is the best structure for sulfuric acid. Let's call it there for this video. In the next one, we're going to briefly look at organic molecules and then talk about bond energies and bond lengths before we jump into VSEPR in the subsequent video. So I'll see you all in the next one.